Wave Theory, Wave Equations series on Electromagnetic Field Theory, lecture number 4.10. Dynamic fields carry wave. This wave is known as electromagnetic radiation. The presence of wave or radiation for the first time was predicted by James Clerk Maxwell by deriving wave equation in dynamic electric field and dynamic magnetic field. Later, after some time, Hedge proved the actual presence of electromagnetic wave, that is radiation. In the present session, our focus is on the derivation of wave equation, its different forms for different media. Let us move further in this endeavor. Wave equation is obeyed by dynamic electric field and also dynamic magnetic field. It indicates the presence of wave or radiation in dynamic fields. EM wave equations, they are available in time domain. They are also available in phasor domain. Each one can be for conductive medium and also non-conductive medium. Time domain equations, they can be derived from time domain Maxwell's equations. Phasor domain equations can be derived from phasor domain Maxwell's equations. Wave equations for non-conductive media can be obtained by simply putting 0 for sigma conductivity in the equations for conductive media. Here are shown different forms of wave equations. Time domain wave equations, phasor domain wave equations. In time domain, free space wave equations that obey free space conditions, wave equations in conductive medium 2 in time domain. Phasor domain also, equations that are valid in free space, equations that are for conductive medium. Certain observations can be made, and these are going to be useful for us to understand wave theory in future. In all the equations, one can see left hand side, it is spatial differentiation, del square E, spatial differentiation, del square H, spatial differentiation. Similarly, all del square E, del square H, del square A, everywhere it is left hand side, it is spatial differentiation. Right hand side, you can see it is time differentiation. Time differentiation. Here also time differentiation, time differentiation, time differentiation, time differentiation. Okay. Of course, in the time domain, right hand side is time differentiation. In phasor domain, time doesn't appear there. Phasor domain means we are having the equations for the situation where time variations are sinusoidal. Right. So basic point is, as far as time domain equations are concerned, left hand side we have spatial differentiation, right hand side we have time differentiation. This is one observation. Second observation, we have two equations, and one is in E, electric field, another is in H, that is magnetic field. The equation for magnetic field can be obtained from the equation for electric field by simply replacing E by H. This observation is valid for all the four cases that are there: time domain, free space, conductive medium, phasor domain, free space, and also conductive medium. After having these two observations, you can see del square E equal to mu epsilon E double dot. E double dot means differentiation with respect to time twice. Single dot means differentiation with respect to time once. So del square E equal to mu epsilon E double dot. Del square H equal to mu epsilon H double dot. Form wise they are similar except for E and H. As far as phasor domain is concerned, del square E equal to minus omega square mu epsilon E. If you replace E by H, you will be getting del square H equal to minus omega square mu epsilon H. Now, there is a connection between this. You can notice a connection. What is that connection? By replacing dou by dou t with j omega in time domain equations, you will be getting phasor domain wave equations. Now, let us move to conductive medium equations. Del square E equal to mu permeability sigma conductivity E dot plus mu epsilon E double dot. By replacing E with H, of course, you will be getting other equation. One more thing you can notice here is, if you replace sigma, this is conductivity, if you replace sigma with 0, or if you give a value of 0 to sigma, then you are moving from conductive medium to free space. Now phasor domain. Del square E equal to gamma square E. Del square H equal to gamma square H. Here a new quantity is there, gamma. What is gamma? This is known as propagation constant. It is a complex quantity having a real part and also imaginary part. Real part is called attenuation constant. Imaginary part is called phase shift constant. We discuss about this constant. It is an important one, significant one. It gives a lot of information regarding wave travel through the medium. About this, we are going to study in this session very soon. Now, time domain wave equation in conductive medium. I have shown in the previous slide time domain wave equation in conductive medium, how it is derived, how we are able to arrive at that equation. Here it is explained. Apply curl on both sides of time domain Faraday's law and combine it with time domain Ampere-Maxwell's law. Del cross E, this is Faraday's law. Del cross E equal to minus dou B by dou T. Apply curl both sides and then combine it with Ampere's Maxwell's law. Then we have this relation. Expand curl E, then we have grad div E minus del square E or Laplacian E, which is equal to minus mu sigma E dot minus mu epsilon E double dot. Of course, we are considering in free space or in a medium where charge density is 0. When charge density is 0, del dot E becomes 0 because del dot E equal to rho by rho, volume charge density, rho by epsilon. When rho is 0, del dot E is 0. When del dot E is 0, this term disappears. You are left with del square E equal to mu sigma E dot plus mu epsilon E double dot. Of course, this is what we want. This is wave equation for E. Similar equation for H can be obtained by applying curl on both sides of Ampere-Maxwell's law and combining it with Faraday's law. Earlier, we first considered Faraday's law and curl is applied. Now we are considering Ampere-Maxwell's law and curl is applying. We are applying curl. It results ultimately same manipulation. So that's why I am not repeating. Notice here form-wise these two are same. Time domain wave equations in non-conductive media. Those are for conductive media, whereas whereas now non-conductive media. Non-conductive media means sigma is 0. By replacing sigma with 0 in the previous equations, we will be getting like this. Del square E equal to mu epsilon E double dot. Del square H equal to mu epsilon H double dot. So these are time domain wave equations for non-conductive media. Phasor domain wave equations in conductive media. They can be obtained by replacing dou by dou T with j omega in time domain conductive medium wave equation. Results del square E equal to j omega mu sigma E minus omega square mu epsilon E. This is equation in E, and similar equation you can be obtained for H also, which is also shown here. Phasor domain wave equation in non-conductive medium can be obtained by replacing or giving 0 to conductivity sigma in phasor domain conductive medium wave equations, and it results in del square E equal to minus omega square mu epsilon E. See, these are same as these equations. The equations that are available with sigma non-zero, from that equations we can obtain these equations by simply considering sigma equal to 0. Now, various forms of wave equations are shown here in a beautiful diagram. If you print this slide in your mind, it will be easy for you to recollect and also to have a kind of connectedness imprinted in your mind among all these equations, right? EM wave equations for free space, sigma equal to 0. For conductive medium, sigma not equal to 0. Time domain, phasor domain. Time domain to phasor domain, one can move by replacing dou by dou T with j omega. Conductive medium, time domain, phasor domain. Time domain to phasor domain, one can move by replacing dou by dou T with j omega. Difference between free space and conductive medium equations is here sigma is 0, here sigma is not equal to 0. So this is able to provide a comprehensive, somewhat complete and total information pertaining various forms of electromagnetic wave equations. Now, a little bit of dwelling on propagation constant. In wave theory, the parameter propagation constant gamma of the medium with units per meter plays an important role. It describes the behavior of the medium with respect to the, in general, it is complex quantity. Real part, imaginary part both exists. Real part is called attenuation constant. Alpha, it is, the symbol is alpha. Units are Nepers per meter, and imaginary part is called phase shift constant. It is denoted by beta, standard symbol. Units are radians per meter. So propagation constant gamma, it is complex. That's why I am using bar here. It is alpha plus j beta. Because it is complex, it has a real part, it has imaginary part also, alpha plus j beta. And already we derived wave equations for conductive medium in phasor domain. From the wave equations, gamma is square root of j omega mu sigma plus j omega epsilon. So propagation constant is j omega mu sigma plus j omega epsilon under square root. This is in terms of constitutive parameters. Gamma in terms of constitutive parameters. But as it is complex, it can always be expressed as sum of real part and imaginary part. Real part is alpha, imaginary part is beta. Alpha indicates attenuation the wave undergoes while traveling through the medium. Beta indicates phase shift that is involved in the wave motion. Some more points we are going to discuss. See, it has a lot of importance in electromagnetic wave theory. Propagation constant is also encountered in transmission line theory. So better we have a clear and deep idea about this particular parameter. If the attenuation is 0, that is, let us suppose the wave is traveling under loss-free conditions. In such case, alpha becomes 0, gamma is simply j beta. When wave motion is not there in the medium, then beta is 0 and gamma is simply real equal to alpha. In such case, see, when suppose we calculated gamma and found that it is pure real. What does it mean? It indicates there is no wave in the medium. Or if it is pure imaginary, then it means wave is there inside the medium. It is traveling without any attenuation. The gamma sometimes after calculation, it may be even complex also. In such case, it indicates that wave is traveling through the medium, okay, but it is undergoing certain amount of attenuation too. So beta pertains to wave motion, alpha pertains to attenuation. When both are there, wave motion is there with attenuation. In general, when wave travels through the medium, it undergoes some non-zero attenuation, and in such case, propagation constant becomes complex. So alpha is non-zero, beta is also non-zero in such case. This is practical case. Alpha, gamma equal to alpha plus j beta is practical situation. Alpha equal to 0, gamma equal to j beta, or gamma equal to alpha. These are all mathematical ideal situations. It is related to constituent parameters of the medium. Gamma is related to constituent parameters. The propagation constant, attenuation constant, phase shift constant, all are related to constituent parameters of the medium. That relation is given here. Gamma is alpha plus j beta. It is equal to square root of j omega mu multiplied by sigma plus j omega epsilon, of course, under square root. Now, after doing some manipulation with this expression, complex algebra, you can divide it into real part and imaginary part. Real part then becomes attenuation constant, imaginary part becomes phase shift constant. So attenuation constant in general, it can be shown after manipulation, it can be shown it is omega square root mu epsilon by 2 into again square root 1 plus sigma square by omega square epsilon square minus 1 brackets closed. Similarly, phase shift constant. Notice only difference between these two expressions, alpha and beta expressions, is alpha contains minus sign whereas beta contains plus sign, except that everything is same. One is plus, one is minus. This is general expression. In case of perfect perfect dielectric, alpha is 0. In case of perfect dielectric, beta is omega root mu epsilon. In case of good dielectric, it is sigma by 2 root mu epsilon. Beta is omega root mu epsilon multiplied by 1 plus sigma square 8 omega square epsilon square. This is for good dielectric. Whereas for good conductor, alpha and beta are same. Notice, they are same. Now, here is shown below the table what is perfect dielectric. Perfect dielectric is one for which sigma is 0, conductivity is 0. What is good dielectric? It is one for which sigma is very, very less when compared to omega epsilon. It is not 0 here. Perfect dielectric, sigma is 0. Good dielectric, it is not 0. I want to tell one important point to you. Sigma is 0 is not achievable. Similarly, sigma infinity is also not achievable. These are imaginary things that doesn't exist in the real world. Always sigma is, it may be small, but it is not 0. It may be large, but it cannot be infinite. In case of good conductor, it is sigma is very, very large when compared to omega epsilon. For these cases, attenuation constant, phase shift constant are the only thing that is required is a little bit manipulation of this particular expression. The attenuation constant, phase shift constant can also be expressed in terms of loss tangent. See, the ratio sigma by omega epsilon, it has a name, it is called loss tangent. It has a symbol, that symbol is tan delta. We have seen alpha is sigma by omega epsilon is there. In the expression sigma by omega epsilon there, but simply replace sigma by j omega epsilon with tan delta. You will be getting alpha in terms of loss tangent, beta in terms of loss tangent. The attenuation constant and phase shift constants in case of good dielectrics. I have given the expressions of these two constants in the table. How those expressions are derived? Here, a brief description of that derivation is given. Alpha equal to, this is general expression, most general expression. This is also most general expression. In case of good dielectrics, sigma by omega epsilon is very, very less. Very, very less. Therefore, using that binomial theorem, this fellow, he replaced sigma square by omega square epsilon square by under square root. He replaced it sigma square by 2 omega square epsilon square. Similarly, here also. Here it is minus 1, here it is plus 1. So now, minus 1 plus 1 gets cancelled. Ultimately, you are getting this one. In case of beta, no cancellation, 1 plus 1 gets added, and once again applying binomial theorem, you will be getting this expression. Propagation constant, attenuation constant, and phase shift constant in case of good conductors. Earlier, we considered good dielectrics. Good dielectrics, now we are considering for good conductors. Good conductor means sigma by omega epsilon, very large when compared to 1. In such case, gamma becomes omega mu sigma by 2 plus j omega mu sigma by 2. So this is a real part. So it becomes alpha. This is imaginary part. This becomes beta. You can find alpha equal to beta. Therefore, alpha equal to beta equal to omega mu sigma by 2 under square. The information pertaining to propagation constant, its various aspects, they are all shown here. This is general defining relation of propagation constant. This is attenuation constant. General, most general terms, most general situation. This is a phase shift constant and most general situation. In case of good dielectrics, attenuation constant. In case of good conductor, attenuation constant. In case of good dielectrics, phase shift constant. In case of good conductors, phase shift constant. This is all I have to share with you for the present.